The lab that we just started recently, the Intelligent Logistics Systems Lab, is an academic research lab that looks into how we can combine machine learning and artificial intelligence with conventional methods that were being used for many decades by now in the logistics industry. And we've always been looking for an industry partner who was willing to actually invest in some of the fundamental research that needs to go into this. And luckily, Mechalux was interested in being that partner for us. So we kicked off this collaboration mostly to basically accelerate research on these advanced new methods and their application in the supply chain and logistics industry.
Great.
And so through this collaboration, we really hope that we can break that ice and we can show a couple of really highly impactful use cases where AI is not just a sprinkle that makes it more interesting, but actually is something that changes the way industry decision making works and also changes the way we as consumers or as customers of certain products or services get to enjoy these products and services, because they might be delivered to us in a faster, less costly, less carbon intense way. So we hope to really accelerate innovation in this industry through this partnership.
Great.
This is a multi-year collaboration, so we obviously had to choose what to focus on in the first year of this collaboration, and we chose essentially two areas of collaboration. One is warehouse robotics, and the other one is what's called distributed order management. So warehouse robotics is actually a very interesting field because unlike some of the futuristic stuff that you might have seen out there around autonomous vehicles or autonomous drones, warehouse robotics is something that's already happening today. So a lot of the talk about autonomous vehicles, for instance, talks about use cases that are still far from wide-scale implementation, partially because of regulatory constraints, but also technology constraints. Within the four walls of a warehouse, you are much more able to control that environment. So that's why warehousing is one of the areas where robotics is already very, very deeply kind of ingrained in many warehouse operations. So what we're doing here is we're trying to make these robots smarter. So for instance, we're trying to make them move in a more intelligent, more human-like way. Because today's solutions are already very good, but they basically still use predefined fixed rules that define their behavior. And so what we're trying to do here is we're trying to develop algorithms that actually learn better policies. So actually let those robots learn how to navigate through a warehouse, much like a human warehouse worker would learn, so through experience, basically. And hopefully by that, through that research, we make sure that these robots operate more efficiently in the warehouse, but also are actually less disruptive. So for instance, disrupt each other less frequently, but also disrupt other human workers or other machines in the warehouse less frequently by, for instance, avoiding collisions early on, or taking paths that are less congested because they already learned through experience that certain paths might be short but prone to disruptions because there might be something in the way. And the second research area is distributed order management. So that's a little harder to explain, but for instance, if you are a retailer and you sell some of your goods online to your consumers, you might actually be fulfilling some of these online orders through a relatively wide network of facilities. These could be warehouses, fulfillment centers, or even the store that you could also walk in as a customer. And so the question is, how do you decide where to fulfill any given order from? And kind of connected to that is the question, like, where do we place inventory? So if I know that I'm going to have online customers ordering certain things, where is the best location for me to store this? Is it in the big box warehouse somewhere outside of a city? Is it in one of my stores closer to the consumer? And in either of these cases, how much of what product should I actually be keeping where? So this is another very complex area of planning and optimization where, again, existing solutions very much build on predefined rules, and we are trying to build basically self-learning systems that gradually optimize over time and learn, for instance, from demand patterns, from customer behavior, what the best way of fulfilling these orders would actually be. One major challenge that we're also trying to tackle in this research initiative is the integration of technology and humans, kind of. So that example that I mentioned earlier about the warehouse robots, the goal is not necessarily to replace everything that has been done by humans so far with robots in that warehouse. There will always be tasks that require human expertise. So the goal really is how can we make the humans and the robots work together in the most productive way. So for example, how can we build robots that are robust to all the randomness that humans bring into the warehouse? Because if you were a fully automated warehouse, you could pretty much tell at any point in time what robot is doing what and moving where. If you have humans moving around, that predictability is not given. So there's a lot of unpredictable elements that humans bring to the table that the robots don't really like. And at the same time, the robots behave in a way that humans don't necessarily anticipate. So making them behave more human-like will make it more easy for humans in the warehouse to actually work together with these robots without constantly conflicting with each other, basically. That's one of the biggest challenges that we see right now already in warehouse operations, but also in future warehouse operations. And that's what we're trying to solve in this lab. We don't just want to throw AI and machine learning as a buzzword to any given problem, because at the end of the day, the logistics industry has been solving some of these problems for many years already, even without machine learning and artificial intelligence. So we're not necessarily looking to completely replace what has been done quite successfully for decades. We're rather trying to find areas where machine learning methods can actually improve or overcome some of the shortcomings that we see in existing methods. And some of these shortcomings relate to the sheer complexity of the systems that we are designing. The example that I made earlier about deciding where to fulfill an order from and where to place inventory, it sounds simple, but if you are running a network, if you're a major retailer who runs a network with maybe dozens of warehouses and hundreds of stores across the country, that decision becomes extremely complex to solve. And existing methods are basically not exactly able to solve that complexity, so we always have to make simplifying assumptions. And those simplifying assumptions lead to things like unnecessary cost, but probably even more importantly to unnecessary product wastage, product obsolescence, and last but not least also unnecessary emissions. We are moving a lot of stuff around the country simply because we're not good enough at deciding where that product should be stored. So overcoming this inability to tackle this huge complexity through machine learning methods is basically what we're striving for in order to save costs, save emissions, improve quality of service to our customers, and overall improve the efficiency of logistics systems.
Excellent.